So for your warm-up problem, there's two ways you can do it, but some people love the ratio test. So let's pull out the ratio test because I think a lot of you guys are doing that. In the ratio test, remember, ratio test can be used to determine intervals of convergence for power series, and that's when you put n plus 1, and that would make that n plus 2 over minus x to the n over 4 to the n plus 1. So the ratio test says look at the limit as n goes to infinity of a sub n plus 1 over a sub n. And so you guys are getting, let's see, minus x to the n times, God bless you, I meant Gesundheit. How do you get rid of hiccups? I take a spoonful of peanut butter. What do you do? You let them go? Do they go away?
Yeah, they go away.
I hate hiccups.
I get them every single day.
Oh no. Oh my gosh. I am just having trouble. I gotta stop talking. Things canceled, right? Lots of things went away, and it gave us the limit. It gave us the limit as n goes to infinity of absolute value of minus x over 4. And the absolute value of a negative is just the positive, so that's the absolute value of x over 4. Those are the same thing. And with the ratio test, what do we need to be true? We need that limit to be less than 1. Now, there are no x's, right? Do you see there's no x's in my limit? So actually, because there's no n's in my limit. And because there's no n's, well, then x over 4 is just a constant. And so this limit is simply going to be the value of that constant because there's no n's to put it into. And we want to say that's less than 1. That creates the inequality, the tripartite or three-part inequality like this. And so I think you guys are all getting that the interval of convergence for this power series would be negative 4 to 4. The other way you could have done it is to look at this as a geometric series. So the other way to do it is look at it as a geometric series. So what do I mean by this? I will only ask you to find a sum of a series if your series is either telescoping or your series is geometric. And people that had recitation yesterday, that's what we did when we did our cards, our little index cards. And those that you guys on Monday, you're going to get to do some index cards. So there's only 2 times when I'll ask you to find the sum of a series. It's when you have a telescoping series or a geometric series. And this guy, is this telescoping or geometric? Yeah, why is it geometric? Because the only place where you see an n is up in the exponent, right? That's how we have the clue that this guy's geometric in form. And so if it's geometric in form, then what is the sum of this series going to be? S equals a over 1 minus r. So we need an a value and an r value. So this is where I would make sure I listed out my terms, okay? So if n is 0, that gives me 1 over 4. Is that right? And if n is 1, that gives me minus x over 4 squared. And if n is 2, that gives me minus x squared over 4 to the 3. But I'm only interested in what is my a value for this power series and what is my r value. And when you have a power series, remember either a and or r might have a letter. And so what is my A value, Max, for this guy? What'd you get? 1 over 4. And James, I think you had the R value.
Yeah, R is negative x.
It is negative x over 4. Beautiful. And so the sum is going to be 1/4 divided by 1 minus negative x over 4. Did anybody simplify this down all the way?
1 over 4 plus x.
And you got, when you get common denominator, what did you get? You got 1 over 4 plus x if we get a common denominator. Let's see. So let me put that extra step in. So down here you could get 1/4 over 4 plus x over 4. That gave you 1/4 4 plus x over 4. Then you flip and multiply and cancel, and that gives you the sum being 1 over 4 plus x. Good.
Now, why are the brackets open for the interval?
So why are the brackets open? Good question. So first of all, because we know it's a geometric series, right? In order for a geometric series to converge, what has to be true? The absolute value of r has to be less than 1. Not equal to, but less than. So that's my clue right there. In a geometric series, it always has to be less than 1. Okay? But now, let's say you didn't recognize that, and you tested, right? That would mean you would put negative 4 back in the original series, and the original series was negative x to the n over 4 to the n plus 1, right? So let's say I put negative 4 in there. I would get 4 to the n over 4 to the n times 4, which is just the infinite sum of 1/4.
That doesn't converge.
And that doesn't converge. Exactly. And the other way, it's alternating, but still the limit is not 0. Yeah. You answered your own question. Very nice. Very good, Andrew. Very nice. Anybody have any questions at all on how to get the sum or the interval of convergence for that power series that's geometric in form? How is everybody? Okay, so what if I said, all right, so we started with a series like this, and we turned it into this. And, well, hang on. Let me show you what that means. What that means is that sum, what did we say that sum was? Sum is 1 over 4 plus x. Yeah, so the thing to recognize about this problem is, first of all, if I have this, it kind of looks like a sum, right? It looks like that idea. Ooh, that's too big. It looks like that idea of a sum. Sum is a over 1 minus r, and 3 over 1 plus x is very similar to that. So 3 over 1 plus x could be equal to my sum, provided a was 3 maybe, and r was minus x. Do you see that? So if we let a be 3 and r be minus x, that could give us that sum. In other words, we could represent 3 over 1 plus x as that infinite geometric series where a is 3, and then the next term is 3 times minus x, and then the next term is 3 times minus x squared, and then the next term is 3 times minus x cubed, right? In fact, we could represent that. Did anybody put it with this summation notation? Did anybody write it like this? It would be 3 times negative x to the nth power, because n is 0, then n is 1.
Why would I start at n equals 1? Or is that just like given to you usually?
Because geometric series, we tend to start them at 0, but we could put it at 1. If we started it at 1, then we would have to put n minus 1 up in the power. So we could do that. Either way, we could do that. Yep.
Okay.
They're equivalent. That's a good question, John.
So if we solve for the interval notation,
We could start it at 1.
It would be equal if we solve for, if we put n equals 1 there. And solve
Let me
for
see.
interval there.
So if we did that, it would be the same thing, right? Because then if n is 1... Yep, those two are equivalent. Yep. My brain just likes to think of it the other way, but you can absolutely start there. But what I'm most important, so I've got the sum of my series, and now what about the interval of convergence? So we know that if this is a geometric series, which it looks like, that means my R value has to be less than 1. The absolute value of the R has to be less than 1. So that means since the absolute value of minus x is just absolute value of positive x, that means I'm looking for x to be bounded by -1 and +1. And so we would say that this is our interval of convergence. And any of those three expressions up here, this one, or this one, or this one, is the sum of that series. Does that make sense?
So you not have to like full out solve it?
There's nothing really to solve, right? This is just, if I was to go to Desmos now and plug in this infinite polynomial and then plug in the sum, on the interval from -1 to 1, I would see that they agreed.
So it'll always be -1 to 1.
For this type of problem.
Yeah.
The last one was a little different, and the next one we're going to do is going to be even more different.
Okay.
Any questions on that? This is our new section, actually, guys, which is representing functions with power series, okay? So this is the whole section, representing functions with power series, all right? And then we have one more after this, and then we're done with material for our course, and we just review and do projects and stuff and exams. But here we go. All righty, so what if we change it up just a little bit? What if we change it up ever so slightly? And instead of 1 or 3 over 1 plus x, what if we changed it to 5 over 4 plus 3x? But I'm just going to put here on the side a over 1 minus r. Still kind of looks like that, doesn't it? Possible. What is the one thing, John, that's in the S formula? A and R's are variables and S is a variable, right? What is the one thing that has to be in that formula to make it all geometric form?
1.
Yeah. There's two pieces, right? We need these pieces here. The A can change, the R can change, but 1 minus has to be there. But we don't have a 1, right? What could we do?
-3.
We could subtract 3, but we have a fraction. If I subtract 3, will that keep the fraction the same? Can I subtract 3 on top and 3 on the bottom and stay equal? No. If I had an equation, absolutely. If I have an equation, I can subtract 3 from both sides. But Andrew, I love your brain. You are on the right track. What could you do instead? I heard Max, you said it. What do you think, Andrew? What else could you do?
Multiply.
Multiply, by, what could we multiply by? To turn that 4 into a 1. 1/4? I love your brain. And can you multiply a denominator and a numerator in a fraction? That's a good question. Like if I have 5 over 15, can I change it to be 10 over 30? Are those equivalent fractions? Yeah, because we're allowed to take and multiply by something. We can also divide by something, so we could divide or multiply by a fifth, right? So we can multiply top and bottom by something. And so if you multiply top and bottom, by 1/4, I think that does it. Just like you guys said. Nice. Now I'm looking at a power series that's geometric in form, and knowing that this is my sum, can you write out that power series? And can you tell me the interval of convergence? So Andrew, this is where it changes a little bit. me wander. So good. So if I expanded this out, excuse me. So you have the absolute value of r is less than 1, which means the absolute value of 3/4 x is less than 1. And that means 3/4 x is bounded by 1 and -1. And that tells you that your interval of convergence, did you guys get from -4/3 to +4/3? And if the homework asks you not for the interval, but what if they ask you for the radius, what would you say? Yep. The radius we know is halfway across the interval. So if our interval goes from -4/3 to +4/3, then the radius is just half of that. Yep. So you would say that the radius is just half of that. Good, 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 good. But I want to show you one more thing on your homework. So on the homework, they're not going to necessarily have you write out this infinite sum. Instead, they're going to ask you for the coefficients of the polynomial. In other words, they're going to say, what is the coefficient when x is raised to the 0th power? What is the coefficient when x is raised to the 1st power? What is the coefficient when x is raised to the 2nd? What is the coefficient when x is raised to the 3rd? So you, on your homework, are just going to put the coefficient pieces, right? So the coefficient piece for the power of x2 is actually 5/4 times -3/4 squared. Do you see what I'm saying? So your homework is not asking you to list out all of the polynomial. Instead, they're simply having you pull off the numerical coefficients, the coefficients that are in front of those powers, okay? So when you input stuff in your homework, that's what you're putting in. Questions? Questions? What do you think? Pretty okay so far, right? Well, let's step it up one more notch. Is everybody okay? Any questions? Everybody's okay. All right, so here's problems 3 and 4. Same instructions. I want to write each of these functions as a power series, okay? And I want the interval of convergence. Same instructions. First one, f of x equals 10x over 12 plus x. And the next guy, f of x equals 3 over 1 plus 25x squared. Same thing. I want to write this out as a power series, okay? And I want to know what is the radius of convergence. Good question. Well, the problem is on that one, no, actually you don't. You don't. And in fact, I think your homework might even write it like this. Something like that. But nope, it's going to be the same goal. The same goal is going to be in play. You need to rewrite that as A over 1 minus R. And note, you can't divide things by x because you don't know if x can be 0 or not. So you can't do any divisions by x. Only divide by numbers or only multiply by numbers. 1 over a number. So when I do it, this is the way I do it. Other people might do it differently, okay? Other people might do it differently. But my whole goal when I look at this is to take that fraction or that rational expression and get 1 minus something. That always tends to be my goal with these. And so if I have 10x over x plus 12, I want to turn it like this and then divide everything by 12. That's what my brain says to me. Turn that into 1. And that gives us 5/6 x over 1 plus 1/12 x. So yeah, multiply top and bottom by 1/12, right? Multiply top and bottom by 1. Is that what you got? Yeah. And then you got your a value in that case to be 5/6 x. And you got your r value to be negative 1/12 x. And you got the sum of the series. So the series you rewrote as a, which is 5/6 x, plus AR plus ARR and where did my power cord go? Hang on. There it is. And what did you guys get as your radius of convergence for that one? You got the radius. Yep. So the radius of convergence is when r is less than 1. And so you said absolute value of 1/12 x is less than 1. Negative 1 is less than 1/12 x is less than 1. And you guys got negative 12 is less than x is less than 12, or the interval of convergence is negative 12 to 12, and the radius is just 12. Now, I want to point something out, though, because when you're doing your homework, you might get all tripped up. You're going to be like, well, I did this in class, we did this in class, and this is what we did. But I want you to look at this power series right here, this summation. Notice it's 5/6 x, and then it's plus 5/6 times negative 1/12 x squared, right? And then it's, here, I'm getting all of this in my space here. Let me rewrite this. This is 5/6 x plus 5/6 times negative 1/12 x squared, and then 5/6 times negative 1/12 squared x cubed. So in your homework, this piece here becomes the third coefficient that corresponds to x to the third. This piece here becomes your second coefficient, or the piece that corresponds to x squared. This guy here is C1, which is the first coefficient that corresponds to x to the first. What are you going to put in for C sub 0? What is the coefficient that goes to x to the 0? Actually, in your homework, C sub 0 means what term do you put with x to the 0th power. Now, normally, that is our a term, right? It's going to be 0, right? But because of the way this power series worked out, we didn't start with our first term just being a constant, right? So you are 100% correct, John. Right here, if there's no if you're starting with x as your first term, you need to put a 0 in here when you type it in your homework, okay? The subscripts correspond to the powers of x as they go. So if you're missing like an x to the 0, you need to put a 0 in there. And that becomes crucial for the next problem, which is 3 over 1 plus 25x squared. And that has a 1 in it right away, right? So what did you let a be? A is 3, and r is negative 25x squared. Is that what you got? Okay, so first thing, let's write out our terms, okay? So if that's how we're going to let a be and what r is going to be, let's write these terms out. Are you with me, right? So it starts with a, and then it gets a times r. And then it gets a times r times r. And then it's a times r times r times r. So the polynomial becomes 3 plus, and then you have what? 3 times negative 25 x to the second, plus 3 times negative 25 squared x to the fourth, plus 3 times negative 25 cubed times x to the sixth. Do you see what happens? Because now my r value is x squared. What terms are dropping out? So on your homework, right, they're asking you for c sub 0. They're going to ask you for c sub 1. They're going to ask you for c sub 2. They're going to ask you for c sub 3. So first thing, what is my coefficient when I have a constant? It's just 3, right? That's my coefficient when there's x to no power. What about when x is to the first power, right? When x is to the first power. Now what's my coefficient? Is it? Hang on. Hang on. Do I have an x to the first power?
No.
No. So my coefficient better be 0. Do I have an x to the second power? Yeah. So what's my coefficient there? 3 times negative 25. Do I have an x to the third? No. So what's my coefficient there? 0 again. Do you see? You have to be very careful when you're doing these, when you start listing them out, that when you list your coefficients in there, those coefficients correspond to the powers of x. Okay?
So if we wrote this out as an actual sum.
Yes. If we wrote this out as an actual sum, it actually becomes more complicated. If we were to write this out as an actual sum, we could write it like this. It's kind of weird and it's kind of strange, but because we only have even powers of x, if we put 2n up there, it captures only even powers of x. But the 25s count, right? They go up by 1s each time, and the 3 always stays there. So if we wanted to rewrite it as a power series, it would look like that. But you're not going to be asked to write that right now. Do you see? But yeah, does that make sense how that would go to that?
Yeah, and we would find the interval and stuff.
Yeah. Well, in fact, you don't even need to do that to find your interval. Here you go. Remember, this is a geometric series, so we're just going to say 25x squared in absolute value has to be less than 1. Now, here's where it gets tricky. The reason it gets tricky now is because this is a polynomial equation, and x squared can't ever be negative, so you can't bound it on both sides by negative. You know what I mean? So algebraically, this thing gets difficult to solve. So I don't know how you learn to solve these in algebra. Does anybody remember by any chance?
First, I would get the x squared by itself.
Okay, let's get the x squared by itself. So divide both sides by 25.
Yeah.
The other thing is x squared is always positive, right? Because x squared is always something positive. So I could remove that absolute value.
Yeah.
And this is what I'm trying to figure out. For what values of x is x squared less than 1 over 25? And at this point, some people might, again, you might be tempted to do this, negative 1 over 25, less than x squared, but you have to, again, be careful because x squared can't be negative. So algebraically, normally what we did was, in algebra class, you would bring 1 over 25 to the left, you would factor, you would find critical numbers, and then you'd test all your boxes in intervals, like we did when we were in Calc 1. Remember how we were in Calc 1 and we would list out factors, and then we'd do test points, and then we would put pluses and minuses, and that's how you learned to do this long ago. I'm just going to say, all right, we've graduated to Calc 2. When is x squared, what's x squared look like? John, what's x squared look like? Do you remember? It's a what? What is x squared? It's a parabola, right? So when is this parabola less than 1 over 25? That's what you're asking. So when is this parabola less than 1 over 25? When is x squared, that picture, less than 1 over 25? That's what we're asking. And where's that happen? Yes. Yes, it is. Because 1/5 squared, right, is 1 over 25. And negative 1/5 squared is 1 over 25. And in between is where that curve, that x squared, falls below that line. And so we would say that this is true on the interval negative 1/5 to positive 1/5. This doesn't apply to our problem, but it's a what if. What if x squared was greater than 125 and we wanted to solve it? What if x squared was greater than 125 and we wanted to solve it? Now what would you get as your solution? See what? There would be something. So tell me.
There would be a union.
So look at your. There would be a union. Yes, there would be. Absolutely. So where is it? Go ahead, John. Give it to me.
Was it negative infinity then negative infinite and then union?
Beautiful. Absolutely. That's a what if, right? We don't have to use that. That was just, oh, well, what if it was changed around and I was getting the bigger part? Do you guys see what I'm saying on this? So these rational, when you get x squared in there, just be a little extra careful. That's the moral of the story. More things are going on than you think. So you would say that your interval of convergence is negative 1/5 to 1/5. And when you listed out your power series, be very careful that you put zeros in place where there's odd powers of x, because there's only evens that work out. All right. Who has questions? Anybody have questions? How are we? Okay. So what does this mean? What does this mean to us? This means that we can take this sum, 3 over 1 plus 25x squared, and write it as this polynomial, right? Okay. Or we can do this guy up here, right? Where we had this. We took 1 over 4 plus x and wrote it as this infinite polynomial. Wow. Watch this. I'm going to write a polynomial up here. Unit series 2 are Taylor and McClaurin. So we're going to look at what's called the Taylor and McClaurin series, all right? The McClaurin series is simply a special case of the Taylor series. So I'm just going to put a note here that the McClaurin series is a special case. Oh, you can't see. Oh my gosh, so sorry. Thank you. Sorry. So the McClaurin series is a special case of the Taylor series. And so I want to just say that, so if I take sine of x, so our goal right now is to represent sine of x as an infinite power series. So first thing I want to do is terminology, okay? Notice that we have sine of x, and we don't have something like this, sine of x minus pi, or sine of x plus 3, or anything like that. We just have sine of x, okay? So when we see sine of x, this guy is said to be centered at the origin, or x equals 0. And we're going to use the letter A as something that we center it with. This A is not the same as geometric series A, okay? We use this A as the centering piece. So when you have A in terms of Taylor series, it means what are you centered about, okay? And so like this guy, we would be centered about pi. If I was to graph sine of x minus pi, it's the sine function shifted over to pi, okay? And in this one here, I would say that I'm centered at -3. This is the sine function shifted over so that it starts at x equals -3. So that's some terminology first. Okay? McClaurin series are series where you're always centering them at the origin. So McClaurin series is simply the Taylor series, but you're centering it at the origin all the time, okay? That's it. So I'm just going to call them from now on Taylor series for now. And if you see the word McClaurin series, just think, oh, it's a Taylor series, but it's centered at 0, okay? So what did this guy Taylor do? He found a formula that will allow us to take any function, if it's differentiable, infinitely differentiable, and turn it into a power series. So the Taylor series, I'm going to write it down, generated by a function f of x centered at the value x equals a can be given by the following formula. And I'll give you this formula on your test, okay? It's the summation k equals 0 to infinity of the kth derivative of f at a divided by k factorial times x minus a to the kth power. And this is true provided f is infinitely differentiable. That means provided f of the kth derivative of f always exists. So f is infinitely differentiable. I am going to tell you that this mathematical formula and statement revolutionized mathematics, just made things go incredibly big and change the world and our understanding of the world. It's powerful, really powerful. So let me actually write this out. So let's write out the Taylor series, at least the first couple terms. So when k is 0, that means take the 0th derivative. Or in other words, just write the function f and plug in the value a. And underneath you would write 0 factorial x minus a to the 0th power. What's 0 factorial, by the way? 0 factorial is 1, right? 0 factorial is just 1, just so we know. And then the next term would be the first derivative of f at a over 1 factorial times x minus a to the first. And the next term is going to be the second derivative of f at a over 2 factorial. And the next one's going to be the third derivative of f at a over 3 factorial times x minus a to the third, dot, dot, dot. You guys see what I'm saying on this? And we would continue forever and ever and ever. So there are 3 pieces to this formula that we're going to focus on. This piece here, which are derivatives. And then we plug in the value a, our center point. The next piece we're going to focus on are our factorials. That piece also always comes into play. And then this last piece over here is our power, right? This becomes our infinite polynomial piece. This is the x to the power. This is what makes this whole thing into that infinite polynomial piece, right? X to some power. So there are 3 parts to this. But hopefully you're now starting to see how we can generate that infinite polynomial. Go back to our Desmos, right? Hopefully you can see that infinite polynomial, how it's going to play out. It's got powers, it's got factorials, and actually, believe it or not, it's got derivatives in there. So let's actually do it. Let's get sine of x and let's represent it as an infinite power series. Alrighty, so we're going to start with sine. And this is going to be my function that I'm starting with. And I want to put out this series. Now, there's a lot of ways to do it. You can set up a table, you can set up a chart. But really, let me just kind of go forward with the Taylor formula. The Taylor formula tells me that if I want to write this as an infinite polynomial, I have to start out with my 0th term, and that's when I have f of a. Okay, so first of all, sine of x, does it have any a value next to it? Is it x minus pi, x plus 3? It's not, it's just x. So what is my a value right now to start? My a value is 0. I'm centering sine at 0, 0. So my a value is 0. So in your formula, everywhere we see an a, we're going to put a 0, okay? So in my first term, so hang on, Tina. So everywhere I see an a, I'm going to put a 0. So why don't I just do that? F of 0 over 0 factorial times x minus 0 to the 0th plus f prime of 0 over 1 factorial times x minus 0 to the 1st plus f2 of 0 over 2 factorial times x minus 0 to the 2nd plus f3 of 0 over 3 factorial times x minus 0 to the 3rd, dot, dot, dot. So that was the first thing I wanted to recognize. We were centering this. This is being centered at a equals 0. And therefore, the value that I'm putting in here into the derivatives and the value that I'm putting next to x has to be 0 for this particular problem. If the homework says center it at pi, then what do? You put pi in there for a. Does that make sense? Okay. Now the next piece, f of 0. So f of 0 is just my function. So really, f of 0 just means what's the sine of 0? Yeah. And f prime is just my first derivative. What's the first derivative of sine? A positive cosine. Positive cosine. So I'm going to take the cosine of 0 over 1 factorial times x to the 1st. Does this make sense? Do you see that? Then I need my second derivative. So what's my derivative of cosine is negative sine over 2 factorial x to the 2nd. And then I need the derivative of negative sine, which is going to be negative cosine over 3 factorial times x to the 3. And then I need the derivative of negative cosine, which is positive sine of 0. And it's going to continue like this forever, right? Beautiful. And let's now replace our sine of 0 and our cosine of 0 and our negative sine of 0 and our negative cosine of 0 and our sine of 0 with numbers. Sine of 0 is just 0. Cosine of 0 is just 1. Sine of 0 is 0. Cosine of 0 is 1. Sine of 0 is 0. And let's put it all together. So what is sine of x? Sine of x can be represented as the infinite polynomial. Oh, check it out. The 0 term just drops out, right? The 0 terms just drop out because 0 times anything is just 0. And that just leaves us with 1 over 1 factorial times x minus 1 over 3 factorial times x cubed. And then the next guy would be plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus 1 over 9 x to the 9th minus 1 over 11 x to the 11th. Are you with me? Do you see the pattern that's unfolding? And where does it come from? It comes from the Taylor series formula, where sine is just being centered at 0. And that's what we did on Desmos, isn't it? And when we plugged that in, it started to grow and make sine grow. The cool thing about this now, okay, so, all right, does this make sense? Do you guys see how we can generate it? Now, I'm pretty sure on your homework, they don't want you to stop there. I'm pretty sure on your homework, they now want you to go one more step, which is to rewrite this as an infinite power. And it's tricky. It's really tricky. It's a little tricky because when I rewrite this, I need to only pull off odd powers, right? Do you see what I'm saying? There's only odd powers. Each time it's only odd powers. But when you run sums, we either start at 1 or 0 usually. But let's start at 1. If I start at 1, how can I rewrite x to the first? Well, that would be x to the n. But then when n is 2, that would be x to the 2, and that's not good, huh? Actually, maybe I don't want to start at n equals 1. Or k equals 1. Maybe I want to start at k equals 0 or n equals 0. Let's see. So if I let x be 2n plus 1, then I could let n equals 0 be my start point, right? And I need to divide these x's by a factorial. And notice the factorials are nice because they match. Do you see how they match the powers?
So it's 2n minus 1, or 2n plus 1 factorial.
Yeah, I could write this as 2n plus 1 factorial. And now I need to alternate it, right? So what do you want to make negative 1 be? Negative 1 to the n. Because when n is 1, then it'll be negative. This is my power series representation for sine. Does that make sense? How are yous? How's everybody feeling? Is that cool or what? You want to try one? You want to try another one? Try one more? Let's try one more. I haven't told you how to get the radius of convergence yet. We'll talk about that next week. You have all the tools because now you just have a power series sitting at you. How do you get the radius of convergence? You use the ratio, or you find R if it's geometric. Unfortunately, this guy's not going to be geometric because each time I'm not multiplying by the same thing. So then I'm going to use what test? The ratio test. So I could use the ratio test on this to find the interval of convergence, but I want to practice. We want to practice that Taylor series one more time. You guys write this in your notes, right? So I can give you a new problem. So what if I said, let's find the Taylor series for e to the x. And again, let's just center that at a equals 0, just for now. Then we can worry about other numbers after, but let's do the same thing. Let's find the Taylor series for e to the x centered at a equals 0. And I'll just write our formula down again so we have it. It's k equals 0 to infinity of the kth derivative of f at 0, because we're centering it at 0. So the kth derivative of f at 0 divided by k factorial times x minus 0 raised to the nth power, kth power, or in other words, that's going to be f of 0 over 0 factorial times x to the 0 plus f to the first of 0 over 1 factorial times x to the first plus f to the 2 of 0 over 2 factorial times x to the 2 plus dot, 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 dot. X, I want to take it up one notch, make it x over 2. So find the Taylor series for e to the x over 2 centered at a equals 0. And so write your function in and then write your first derivative in and then write your second derivative in. You know what I mean? Sometimes it's helpful if you put your derivatives going down. If that makes sense. So sometimes that helps. And then putting the next column to set you up would be then plugging 0 in. So sometimes that helps when you're, expanding it out and writing out your expansion. Sometimes it helps to keep these derivatives separate. Sometimes it helps to keep the derivatives a little separate. Turns out to be 1. So you're right. That just becomes 1, and then 1/2, and then 1/4, and then 1/8, and 1/16. So that's kind of cool. That's kind of cool how that works out on this. And those pieces are my derivative pieces. both 1/2 and x would have to be in the parentheses, right? Yeah. So you could rewrite it. I like it. You could rewrite it like n equals 0 to infinity of 1/2 to the nth x to the nth over n factorial. You could do it like that. Does it go down? So 2 factorial, that could give us something. And 3 factorial, that could give us something. Do you see what I'm saying? So I believe it might, I don't know if it's possible, but if this guy's 1, is it possible to reduce these? I'm not sure. 2 factorial is 2. So 1/4 and 2, oh no, that's not going to give me anything necessarily nice. 3 factorial is 6, so that's going to be 6 over 8. Oh.
Yeah, they don't really reduce it.
They don't really do anything funky, do they? 4 factorial is 4 times 3 times 2 times 1.
24.
What's that? Oh, yeah, you're right. I don't think they do anything funky there. I was trying to see if it would give you any pattern, you know, if you reduced it down. But I like it. How do you guys think? What do you think about Taylor series? They're okay. They're not bad, huh? Now, what I could do is go on, right? I could find what's my radius of convergence by using the ratio test. I could actually type in Desmos, this infinite polynomial, and it's going to go towards E over time for that radius of which I could get my convergence. And so to get your radius of convergence, if I wanted to go from there, I would simply use my ratio test. And I'll just put a little note. And when we come in on Monday, we'll practice more of that. Next Wednesday, we'll have a group quiz on everything for our test. And then we'll do our test 4. And then the following week, we're going to have fun. We're going to do projects. And those grades will go towards your final grade. And we'll also review for your final.